KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we are going to discuss one example problem, that is what example 7.7. Afterwards, we are going to discuss the topics of, that is what principle of movements and then center of gravity, right? The first is principle of movements and then center of gravity, okay, right. First we will go through example 7.7, okay, right. See here, you know, this is what show that movement of a couple doesn't depend on the point about you take the movements. You know, childs are playing a seesaw. There is what in our park, right? In our park, the children are playing seesaw. That is what one child is sitting on one side and another child is sitting on another side, and they used to move up and down, right? So that is what you just imagine, to understand this problem. So here, the movement he is asking in this problem, he is asking movement of a couple. Generally, couple means what? Two, right? A pair of forces. So here, even in this, you see this picture. Here also, we are seeing a pair of forces, right? That is what, see here. Here one force and here one force, right? So for our identification, this is what F means. It is what minus F, because of acting in opposite direction. That is the only thing, right? No other meaning. Okay. See. So the movement of a couple. You know, movement of a couple means, how can we understand the word, right? So movement of a couple means two forces, right? Suppose for example, if you open a water bottle, there also we need to apply two forces now, right? So wherever you apply two forces and which cause the rotational motion, right, about a point, and you know, what is the resultant of these two forces acting? That is what is the movement of the two forces? What is the movement of the two forces, right? That's what he is asking. So that movement of a couple doesn't depend on the point about you take the moments. Okay, right. See this. You see this picture. That is what here. Couple, this is what force and this is what another force, right? So this is the couple and acting on the rigid body, right? So this is what rigid body, couple is acting on the rigid body. The forces F and minus F act respectively at points B and A, right? These points have position vectors. These points have position vectors R1 and R2, with respect to origin O, okay, right. So let us take the moments of the forces about the origin. And you see this statement, that is what like relation or equation, that is what the moment of the couple. The moment of the couple is equal to sum of the moments of the two forces making the couple. Moment of the couple is equal to sum of the moments of the two forces making the couple. That is what we can write it as, see here, that is what we can write it as R1 into minus F plus R2 into F. So this is what minus F and this is what F, right? So finally you can write like this, no, that is R2F minus R1F. That you can write like this, no, R2 minus R1 into F. So what is the moment of the couple? R2 minus R1 into F, right? And from this you can also write that is what R1 plus AB is equal to R2. This is what R1, this is what AB is equal to R2. So what is AB? R2 minus R1. R2 minus R1. So that you write this one in this equation. That is what the moment of the couple. So if you write these things in this equation, then what is the final answer? The moment of the couple therefore is, the moment of the couple therefore is AB into F. AB into F. That is what product of either of the force, product of either of the force and perpendicular distance between the two forces, right? So this is AB is the distance between the perpendicular distance between the two forces, no? So the moment of the couple therefore is, so product of either of the force, I mean here you have to take only magnitude, right? Product of magnitude of either of the force and perpendicular distance between them, right? So this is what example 7.7. Next, see, now we are going to discuss that is what principle of moments. Principle of moments, okay, right? So observe carefully, this is what in our daily life we overcome. So just now I told you to take seesaw as an example while discussing example 7.7, right? So here also while discussing this principle of movements also you take the same seesaw as an example. Movement, taking or getting the rotational motion or translation, whatever it may be, right? Principle of movements, okay, right? An ideal lever is essentially a light rod, right? An ideal lever is essentially a light rod pivoted at a point along its length, right? So what I am saying, you please keep in mind, that is what just like you just imagine, okay, just a minute, okay. See here, see this picture, right? This is what when I am saying this one, you just observe here, the lever is a system, right? And before that I will tell you, an ideal lever, right? An ideal lever is essentially a light rod pivoted at a point along its length. See here, this is what pivoted here, and it is the light rod, okay. This is the length of the rod, okay. And this point is called as fulcrum, okay, full stop. A seesaw on the children's playground is a typical example of a lever, I already told you. And here also, two forces F1 and F2, and see the moment of forces also, right? Two forces F1 and F2 parallel to each other and usually perpendicular to the lever. So this is also perpendicular and this is also perpendicular to the lever. Act on the lever at a distance. Act on the lever at distances D1 and D2. At distances D1 and D2 respectively from the fulcrum. At a distance D1 and D2 respectively from the fulcrum. So what are these distances D1 and D2? Distance of force F1 and distance of force F2. So this is what D1 and this is what D2, okay, right. And now you observe carefully, the lever is a system in mechanical equilibrium. The lever is a system in mechanical equilibrium. Let R be the reaction. Let R be the reaction of the support at the fulcrum. At the fulcrum. And R is directed opposite to the forces. R is directed opposite to the forces F1 and F2, right? So for translational equilibrium, right? Yesterday we discussed what is translational equilibrium, what is rotational equilibrium, right? So regarding the translational equilibrium, R minus F1 minus F2 is equal to 0 because this is R, this is F1, this is F2, right? So simple, I can write R minus F1 plus F2 is equal to 0. R minus F1 plus F2 is equal to 0. But you can also write like this, that is what R minus F1 minus F2 is equal to 0. This is for translational equilibrium. But what about the rotational equilibrium? What about the rotational equilibrium. This is what equation for rotational equilibrium. d1 f1 minus d2 f2 is equal to 0. d1 f1 minus d2 f2 is equal to 0. This is what the sum of the moments must be 0. To keep this lever in rotational equilibrium, the sum of the moments must be 0. That is what d1 f1 minus d2 f2 is equal to 0. And here generally anti-clockwise movements are taken to be positive, that is clockwise to be taken negative, right? Anti-clockwise movements are taken to be positive and clockwise to be taken negative, right? That is what. Okay. Next, if you observe carefully here, the fulcrum itself has 0 moment, right? So this R acts at the fulcrum, itself and has 0 moment about the fulcrum. So that is what we are talking about equilibrium now. So it is what translational equilibrium and it is what rotational equilibrium. Okay. And this equation, that is what we are having, like equation 1 and equation 2, we are getting from the conditions of equilibrium. So either for translational or for rotational, these two equations we are getting from the conditions of equilibrium. And in the case of lever, force F1 is usually some weight to be lifted. It is called the load. This is called the load, right? So when it is load and this distance is load arm, and this is called as effort, and this is what effort arm. So D2 is the effort arm. Right? Okay. And equation 2 can be written as, this is what the same equation we are writing, d1 f1 is equal to d2 f2, right? Okay. And load arm into load is equal to effort arm into effort. Just by seeing this you can see, right? Load arm into load is equal to effort arm into effort. That is what we are getting from this equation, right? And here itself we can define mechanical advantage. That is very, very important for us. That is very, very important for us, right? That is very, very important for us. You see here mechanical advantage. So in short form I have written that is what MA is equal to F1 by F2 is equal D2 by D1. See here, from this we are writing F1 by F2 is equal to D2 by D1, right? So this above equation expresses the principle of movements for a lever, right? This is what principle of movements of a lever, and there is a relation between these two, but we are defining that. Mechanical advantage is the ratio of these two. When we are getting the ratio of these two, that is what this we can write in terms of D2 and D1. That is what F1 by F2 is equal to D2 by D1. Okay, right. So if the effort arm D2 is larger than the load arm, if the effort arm D2 is larger than the load arm, if the effort arm D2 is larger than the load arm, the mechanical advantage is greater than 1, right? So when D2 is greater than D1, that is what effort arm is larger than the load arm, the mechanical advantage is greater than 1, right? So that is what mathematically I am saying. Okay, right. So when the mechanical advantage is greater than 1 means a small effort can be used to lift a large load. Small effort can be used to lift a large load. Okay. And there are several examples for this situation. That is what seesaw and beam of balance. Beam of balance is also a lever, right? And here itself we have to discuss about the next thing. That is what center of gravity. Center of gravity. Okay, and here itself, center of gravity also plays an important role here. Not only here, in our coming discussions also, right? So the next thing regarding this principle of movements is center of gravity we have to discuss. So what is center of gravity? Already we discussed the center of mass in the starting of this chapter. That is what rotational motion, right? So after completion of introduction, we discussed what is center of mass and how to find the position of center of mass. How to find the position of center of mass we discussed. Okay, right. So after completion of that center of mass, it is easy to discuss center of gravity, right? Okay. So center of gravity is an imaginary point. Center of gravity is an imaginary point where the total weight of an object. Center of gravity is an imaginary point where the total weight of an object supposed to concentrate. Center of gravity is an imaginary point where the total weight of an object supposed to concentrate. Supposed to concentrate. Okay, right. You can see this one. That is what. See, balancing a cardboard. It is what cardboard, ma. So balancing the cardboard on the tip of a pencil. This is the pencil, and it is the tip of a pencil, right? And the point of support G is the center of gravity. This is what center of gravity. Okay, and you can see one more picture just beside this. This is what determining the center of gravity of irregular shape. Right? The center of gravity G lies on the vertical line A1, right? On the vertical line, that is what A1. Okay, so this is what A, and this is what A1 or A dash, whatever it may be, right? So naming, that is our wish. If you want, you can call it as PQ, no problem. Okay, right? So this point is A, and this is what A dash, right? So the center of gravity lies on the vertical line of A1. Okay, and through the point of suspension of the body. So this is the point of suspension. This is the point of suspension, and this is the irregular shaped body, and it is a picture which gives information while finding the center of gravity for irregular shaped body. Okay, right. So just now I told you what is meant by center of gravity. So center of gravity is an imaginary point where the total weight of an object supposed to concentrate. Okay, right. And not only this one, even in our class also, you seems to play with the pad, exam pad, right? So just you are taking one exam pad and you are concentrating that exam pad on the finger, on the forefinger, and you are trying to rotate the exam pad, right? So how it is possible? That is possible because you kept the finger, right? You kept the finger at the center of gravity, of the exam pad. Okay, but exam pad is what regular body, because it is in a rectangle shape, right? And what about the bodies which are available in irregular shape? That is also points, right? And at the same time, you also concentrate on different types of bodies. Different types means basically different shapes, right? So what is meant by regular bodies? Rectangle shaped, circle shaped, square shaped, right? Triangle shaped. These and all, we are providing some shape, means we are calling it as a regular body, right? So by saying one body, we are not attributing any shape. We are not giving any shape. Then which is called as irregular shaped body. Okay, that is the only difference between regular bodies and irregular bodies. Okay, right. And you just take an irregular shaped cardboard, right, and a narrow tipped object, that is like a pencil, right? You can locate by trial and error a point G on the cardboard where it can be balanced on the tip of the pencil. So what he is saying is, with the help of trial and error method, you can find out the center of gravity for an irregular shaped body. So here irregular shaped cardboard. Okay, that is what he is saying. So this point of balance is the center of gravity of the cardboard. The tip of the pencil provides a vertically upward force due to which the cardboard is in mechanical equilibrium. So this is what this tip of the pencil provides, right? Vertically upward force. Due to that, the cardboard will be in mechanical equilibrium. That only we are expecting. Okay, so the cardboard will be in mechanical equilibrium. Okay, right. So by seeing this figure, that is what. By seeing this figure, the reaction of the tip is equal and opposite to mg. So this is what mg, so which is the weight of this irregular shaped cardboard, and the tip of the pencil, it is the tip of the pencil which balances this force, and the total weight of the cardboard, and hence the cardboard is in translational equilibrium, right? And because of balancing this tip of the pencil to this weight, the cardboard is in translational equilibrium. And because of the providing vertically upward force by the tip of the pencil, it is in mechanical equilibrium, right? So finally the cardboard is in equilibrium. That only we want to know. Okay, by concentrating like that, you are making the irregular body to rotate means, okay, that I will come to the point. But now what I am saying is, you are holding an object at the tip of your finger or at the tip of the pencil means that will be in both the translational and that is what mechanical equilibrium. And now itself we can say that it is in rotational equilibrium. Okay. When it doesn't happens, when it is not happening, when it doesn't happen, so what can we say? Due to the unbalanced torque, it would tilt and fall. Generally, we experienced, right? We don't know all this information, but we experienced practically what happens when we focus to keep, when we are interested to keep the body in translational equilibrium, mechanical equilibrium, and finally it will be in rotational equilibrium, and which is also in rotation. Okay, right. So there are torques on the cardboard due to the forces of gravity like M1G and M2G. But what will happen? Balancing each other, acting on the individual particles that make up the cardboard. Okay, so there are torques. That is what perpendicular distance into force. Next, see here, the center of gravity of the cardboard is so located. The center of gravity of the cardboard is so located that the torque, that the total torque, the center of gravity of the cardboard is so located that the total torque on it, due to the forces M1G, M2G, etc. is 0. Okay, that is what he is talking, right? And now, if Ri is the position vector of the ith particle of an extended body with respect to its center of gravity, then what is the torque about the center of gravity? Due to the force of gravity on the particle, that is what tau I is equal to Ri into Mi into G. And if you take the total gravitational torque about the center of gravity, then it will be 0. That will be 0, and you can write this expression, that is what sigma tau I is equal to sigma Ri into Mi into G is equal to 0. This is what torque due to the gravitational force, which is called as gravitational torque. Okay, and here itself we can define the center of gravity as that point where the total gravitational torque on the body is 0, right? So generally what I told you, center of gravity means imaginary point where the total weight of an object supposed to concentrate, right? Here you can say that the point where the total gravitational torque on the body is 0. Total gravitational torque on the body is 0. Okay, and one more thing, this is what from this equation you can say that G is same for all particles, and right, at the same time G is same for all particles, and hence it comes out of the summation. This gives G is non-zero. You can write it as sigma Mi Ri is equal to 0, right? When you are taking this one out because it is constant, no, then you can say that sigma Mi Ri is equal to 0. Okay. So remember that the position vectors are taken with respect to center of gravity. The position vector, suppose here means like R1, suppose here means like R2, whatever it may be the point. There are n number of particles, right? Not only 1 and 2. So from M1 to Mn, M1 to Mn. Okay. So in accordance with the previous information, that's what we discussed, right? If the sum is 0, the origin must be at the center of mass of the body. If the sum is 0, and if the sum is 0, the origin must be at the center of mass of the body. Thus the center of gravity of the body coincides with the center of mass in uniform gravity or gravity free space. In uniform gravity or gravity free space. Okay. So this is true because the body is being small. G doesn't vary from one point of the body to the other point. G value changes from one point on surface of earth to another point on surface of earth, not from one point of the body to another point of the body, right? And if the body is so extended that G varies from part to part of the body, means it is very big, that is like kilometers and kilometers, right? So when you take such type of body, then G value changes, then the center of gravity and center of mass will not coincide. So in case of small bodies, in case of regular bodies, we are not sure about the coincidence of center of mass and center of gravity. If the body is big, we are not sure. Okay. So basically the two are different concepts. That is what center of mass has nothing to do with gravity. It depends only on the distribution of mass of the body. That's we already discussed. When we were in a discussion about center of mass, there I told you center of mass is an imaginary point where the total mass of an object is supposed to concentrate, and this point depends upon the distribution of mass of the individual particles. Okay, that's what I told you. Next, see the position of the center of mass of several regular homogeneous objects, right? So that you can see, because the objects are not limited now. You know, table, that is what, book, and exam pad, and chalk piece, and duster, whatever it may. We have different and various objects. We can discuss about that is what center of mass of several objects in our coming classes, when we are going to discuss about, you know, moment of inertia, right? Moment of inertia is analogous to inertia in translational motion. So in translatory motion, how we discuss the inertia, similarly in case of rotational motion, that is what the moment of inertia came. Moment of inertia came to the picture. Okay, that's what. So here another way of determining center of gravity of an irregular shaped body like a cardboard, you can see, if you suspend a body from some point like A, right, the vertical line through A passes through the center of gravity, we mark, right? This is what he is saying. So you can find like this. So first you have to take, that is what, a body, and you suspend the body from some point like A. This is A, right? After suspending, the vertical line through A passes through the center of gravity. We mark the vertical line, that is A1. Afterwards, you suspend the body from B, and then you do the same thing, that is what, B1. Afterwards, you suspend the same body at C and repeat the same process. You will get it as C1. So these three are the pencil lines, no? So we draw the lines with the pencil or pen. Afterwards, we are going to, these all are going to meet at a point. That point is the center of gravity. That point is the center of gravity. Okay. So this is body is small, no? That's why this method is enough, and this method is allowed to determine center of gravity. Okay. So that you can also find, to find center of mass, and I already told you, in case of small bodies and regular bodies, center of mass and center of gravity coincides each other. Okay, right. So in this class, we discussed one example problem, and afterwards we came to discuss the principle of movements. There itself, the important thing we discussed, mechanical advantage, right? You know, in our daily life, when you are doing some work, your parent or your brother came and do the same thing by spending less amount of energy and shortest time, in shortest interval of time. That is what he is getting mechanical advantage, right? You know, once upon a time, we used to get the water from a well, right? Afterwards, we had hand pump. Nowadays, we are having tap, right? So once you imagine how much mechanical advantage we got it, right? So by spending little amount of energy and with small effort, you have to get more, that is what, we have to do a lot of work. That is what, high mechanical advantage. Okay, right. Afterwards, we discussed the center of gravity. Okay, ma? Right. Thank you. We will continue in the next class.